So the easiest way to tell which one is which is to plot the data. So if we have a set of data here, so let's say concentration of something, and over here we have not concentration of time, but just time, right? And so we've got some numbers here all the way down. The easiest thing to do is to plot them. So make a graph here that is just concentration versus time. Make a graph of 1 over concentration versus time. And then make a graph of natural log of concentration versus time. One of these will give you a straight line. The one that gives you the straight line is represents the order of the reaction. So if it's natural log, this is first order. If it's just straight concentration versus time, this is 0th order. And if it is 1 over, then this is second order. The other way you can tell what order it is by looking at the rate constant. All right. So we know that rate is equal to rate constant K times the concentration of the components to some power. And the sum of the exponents there is the overall order of the reaction, right? We know that rate has to have units of moles divided by liters second, right? Because it's a change in concentration with respect to time. We know that each one of these concentrations has units of moles per liter, but they're raised to some power, right? So here we're going to have some units for K. We don't know what it is yet. And over here, we're going to have some units of moles per liter raised to the overall order, right? So then the question is, what are the units on K? Right? So let's just solve this thing for K. So I'm going to write, if you guys will allow me, this M plus N, I'm just going to write it as order, okay? So we'll say up here, let order equal M plus N, okay? Okay, so how do we do that? So K then will be equal to moles divided by liters times second, and then that divided by moles per liter for the order, right? So now let's clean this up a little bit. So here we'll get, if I take the 1 over seconds out, I can say that this is just going to be seconds to the minus 1. That's the same thing as 1 over seconds. And then I've got here moles divided by liters. And I'm dividing those things and they're raised to different powers, right? So math says that this should be 1 minus order. Do you agree with that? But we don't really like to write it this way. We usually see this written not as moles per liter, but as liters per mole. So I'll just flip that thing, all right? When I flip that thing, that puts a minus sign in front of the exponent. Do you agree with that? So this becomes seconds to the minus 1, liters divided by moles. And now this is minus, and in parentheses, 1 minus order. So we distribute the minus sign through, and this becomes order minus 1. So the units of my rate constant are going to be this. So I can get the order of the reaction by looking at the units of the rate constant. So if I see something that has units of seconds minus 1 only, what's the order of the reaction? Another way to ask that is, what value do I put in for order right here to achieve only seconds to the minus 1? If I put a 2 in there, then that becomes seconds to the minus 1, and then liter per mole raised to the 2 minus 1. So that would be liter mole second. So seconds to the minus 1, this is first order. Right? Plug a 1 in for order, and you have seconds to the minus 1 multiplied by liters per mole to the 0 power. Anything to the 0 power is 1. So if you see seconds to the minus 1, this is first order. What would it be for second order? Well, you just told me throw a 2 in there, right? What do we get when we throw a 2 in there? Well, 2 minus 1 is 1, right? So this is going to be liters per mole, and then multiplied by seconds to the minus 1. Well, what we usually see this written as is liter per mole second, like that. And what would it be for 0th order? That's it. Mole per liter second. So that's two different ways you can determine the order of the reaction by looking at the data. Right? We can plot the data itself if we have it, or we can look at the units of the rate constant. Either one will give us the order of the reaction. Why do we have rate orders? So when we have mechanisms, the orders have to do with how many molecular events are happening, right? So if two things come together, that's bimolecular, that's second order. And then when we have lots of steps in a rate law, the rate determining step of the mechanism is the slowest step. And that determines the rate of the overall chemical reaction, or the order of the overall chemical reaction. So it goes back to how many things are happening in the chemical reaction, right? In the slowest step, how many molecular events are happening? Once we have those orders, we have concentration versus time relationships for those orders, right? We have for first order, we have that the concentration of A at time t is equal to the concentration of A at time 0, e to the minus kt. And for second order, we know that 1 over the concentration of A at time t is going to be equal to kt plus 1 over the concentration at time 0. So this is where those graphs come from. I said, hey, plot those things, and the one that gives you a straight line. So we could write first order in a straight line form. It would be natural log of A is equal to minus kt plus natural log A0, right? And so what you get here, if you plot natural log A versus t, you get a straight line. The slope here would be minus k. In this one, you plot 1 over concentration versus time, and the slope here is just k. Right? So in the lab, this is how you would do it. You would plot the data, right? You take the data, concentration data as a function of time, and then you would plot it, and the one that gave you a straight line would be the order, and then the slope of that line would tell you the rate constant. Right? The intercept of that line tells you the initial concentration.